One really cool thing about Spark is that it has methods for doing machine learning and data science at very massive scales using a cluster, so that's kind of cool. It's called MLLib, stands for Machine Learning Lib. Let's talk about what it can do. So it's a little bit tough to talk about MLLib if you don't have some sort of a background in machine learning or data science. I do offer a course on that, a little plug there, but here are some of the basic things that MLLib can do today. And this list is always expanding, so they're always figuring out clever ways of actually distributing some of these algorithms. It's not easy. Not all machine learning algorithms really lend themselves to being distributed, but they've figured out quite a few of them. One thing it can do is feature extraction, so TF, IDF, term frequency, inverse document frequency, basically a fancy way of breaking up documents into features, words, and figuring out how the probability of a word correlates to a given document. That's basically a useful thing for doing search. Okay, so if you're implementing some sort of massive search algorithm, MLlib could be useful in actually processing your documents into data that can actually be used for search. It also has methods for basic statistics, chi-squared, correlation coefficients, simple min, max, mean, variance. Honestly, you probably don't need MLlib for that sort of a thing. It's pretty simple to do anyway, but if you're going to be using MLlib anyhow, it does offer quick ways of doing those sorts of things. Linear regression and logistic regression, very common thing to do in data science. Basically, you want to fit a bunch of data to a line and use that line to predict values that you haven't seen yet. So let's say you have some data set of something plotted against something else, like, I don't know, age and income or something, or anything you can dream up. If you think there might be some sort of linear relationship between these two things, you can use linear regression, for example, to get a line equation that fits the data, and then use that line to predict, say, income for ages you haven't seen before. So MLlib can help with that at large scale as well. Support vector machines, basically a way of doing classification in multiple dimensions, a little bit beyond the scope of this course. Naive Bayes classifiers, a common example of that is a spam filter. So you can actually train a naive Bayes classifier with a bunch of email data that's known to be classified ahead of time as spam or not spam. And after training on that data, you can apply that classifier to new emails to try to predict if they're spam or not. So you can build a very simple spam filter using naive Bayes. And MLlib gives you a way of scaling that out to a cluster if you're going to deal with a massive email data set. Or email is just one example of it. Decision trees, cool stuff. That's basically a tree of decisions based on how to actually predict something given, a chain of data. So one example I've seen recently is basically a decision tree of who will win the presidential election in the United States in November of this year. And there's a decision tree that shows, okay, well, if Trump wins Florida, there's this set of decisions that can lead to a certain outcome. And if Trump loses Florida, there's another set of decisions that can lead to a different outcome. And little aside, I live in Florida, and it turns out Florida is, in fact, the biggest deciding state there. But MLlib, if you have some massive set of data that you need to construct into a decision tree, it can help you do that as well. K-means clustering, also something that MLlib can distribute for you. It's just a way of automatically clustering data. It's an unsupervised learning technique, meaning that you don't have to actually train it on real data. It can just look at a spread of data points and actually try to cluster them together into areas that seem to be like tightly correlated. It's up to you to figure out what those clusters mean, but sometimes it can help you sort of discover genres in music or things like that. Principal component analysis, singular value decomposition. These are all what we call dimensionality reduction techniques in data science. Basically, if you have a lot of different features of a given data and you want to boil that down to something you can more easily visualize or process, these are techniques for doing that. For example, an example that I use a lot is flowers. Let's say that you want to be able to predict the species of a flower based on 4 attributes: the length and width of a petal and the length and width of a sepal. Well, it's kind of hard to visualize 4 dimensions of data, but with SVD or PCA, you can boil that down to a lower dimensionality set and actually visualize that data and look for clusters in a lower dimensional space. And finally, we can also do recommendations using a technique called alternating least squares, and we're going to do that as part of this lecture. So earlier in this course, we actually found movie similarities using our own algorithm written from scratch without using MLlib, and the results were pretty good. So we could say, for example, if you're a person who likes Star Wars, you might also like The Empire Strikes Back and Indiana Jones. And we got some pretty good results there. Well, a while ago, there was actually a contest run by Netflix called the Netflix Challenge. They used to have their own recommendation algorithm, and they had a little contest where they would award, I think it was $1 million to anyone who could improve upon their existing algorithm in an existing way. And one of the winners was based on a technique called alternating least squares. So let's see if that actually does outperform the way we did it. Now, MLLib introduces some specialized data types you have to use that we'll take a look at. One is the vector class. One thing you see a lot in data science and machine learning is that you have these big arrays of information where you have a lot of missing values or empty values. And a sparse vector is a way of compactly representing that sort of a thing. So, for example, if I have a vector of all of the movies ever made and I'm keeping track of the ratings for an individual, odds are an individual has only actually rated a handful of those movies. So we can much more compactly represent that vector of ratings as a sparse vector that only contains the movies that person actually rated. Label point, idea there is if you're doing a supervised machine learning where you basically want to predict the label for a given point. Label point is a way of associating a label with a point, where a label might be some classification like genre or race, income range, whatever you can dream up, right? And rating, something we're going to use right now, for example, a rating of a user for a given movie. If you want more depth on MLLib, a good book I like is Advanced Analytics with Spark by O'Reilly. So go check that out and pick it up if you want to learn more about MLLib in action. Very good book and lots more examples in there too. So with that, let's go make some movie recommendations. And the nice thing about MLLib is just how darn easy it is. So look at this. Just a handful of lines of code, and that's pretty much all you need to make movie recommendations using MLLib with the Movie Lens dataset. So here we're just loading up the u.data file from the ML100K dataset into a data RDD. We're mapping that into rating objects. Remember, rating is one of the new MLLib data types. So we're basically creating a rating object for each line that has the user, movie, and rating. And we're stuffing that in a ratings RDD. And we're going to cache that because MLLib is going to use that data multiple times. Finally, we just call als.train with a couple of parameters here that we've chosen to actually generate a model that can recommend movies for individuals based on all those ratings. And with basically one line of code, we have that model back, and we can actually call recommend products on that model for a given user ID. So this is saying I want the 10 best recommendations for a given user ID based on the model that I made from all these ratings. And that's all there is to it. So deceptively simple, It's I kind of look at black boxes like this a little bit skeptically, and let's see if that skepticism is founded. So let's actually run this, see what kind of results we get.